Welcome to this structured Class 10 science lecture on carbon and its compounds. Carbon is one of the most versatile and fascinating elements in the universe. Although carbon makes up only 0.02% of the Earth's crust in the form of minerals like carbonates and coal, and 0.03% of the atmosphere as carbon dioxide, it forms the chemical backbone of all living organisms. The food we eat, the clothes we wear, the medicines we take, and even our own DNA are all based on carbon. The chemistry of carbon is so vast that it is studied as a separate branch called organic chemistry. In this lecture, we will explore why carbon forms covalent bonds, investigate its versatile nature, master the nomenclature of hydrocarbons, explore functional groups, and study everyday compounds like ethanol, ethanoic acid, soaps, and detergents. The atomic number of carbon is 6, meaning it has 4 electrons in its outer valence shell. To achieve a stable octet, carbon must either gain or lose 4 electrons. However, gaining 4 electrons to form Ac4- anion is difficult because 6 protons in the carbon nucleus cannot easily hold 10 electrons. Similarly, losing 4 electrons to form Ac4+ cation requires an enormous amount of ionization energy to overcome nuclear pull. To resolve this, carbon achieves stability by sharing its valence electrons with other carbon atoms or atoms of other elements like hydrogen, oxygen, nitrogen, and chlorine. This sharing of electron pairs between atoms constitutes a covalent bond. Covalent compounds have low melting points because of weak intermolecular forces, and they do not conduct electricity because they form neutral molecules without free ions. Carbon forms an exceptionally large number of compounds due to 2 unique properties, catenation and tetravalency. Catenation is the unique ability of carbon atoms to link together through covalent bonds to form long, stable straight chains, branch chains, or closed rings. No other element exhibits this property to the extent that carbon does. The second property is carbon's tetravalency. Having a valency of 4, a carbon atom is capable of bonding with 4 other carbon atoms or monovalent atoms of other elements. Furthermore, because of its small atomic size, carbon forms exceptionally strong and stable covalent bonds, as the nucleus holds the shared electron pairs tightly. This allows carbon to form single, double, or triple covalent bonds, leading to millions of stable organic molecules. Hydrocarbons are organic compounds composed entirely of hydrogen and carbon. They are divided into 2 main categories, saturated and unsaturated hydrocarbons. Saturated hydrocarbons, also known as alkanes, contain only single covalent bonds between carbon atoms. The simplest alkane is methane, followed by ethane. Their general molecular formula is CnH2n+2. Alkanes are generally unreactive. In contrast, unsaturated hydrocarbons contain double or triple covalent bonds between carbon atoms. Those containing a double bond are called alkenes, with the general formula CnH2n. Those containing a triple bond are called alkynes, with the general formula CnH2n-2. Unsaturated hydrocarbons are highly reactive and undergo addition reactions readily. A homologous series is a family of organic compounds that share the same functional group and general chemical properties, with successive members differing by a CH2 group. For example, the alkane series starts with methane, followed by ethane, propane, and butane. Each member differs from the next by a molecular mass of 14 unified mass units. As the molecular mass increases in a homologous series, we observe a gradual gradation in physical properties. For instance, the melting and boiling points increase systematically because the intermolecular van der Waals forces increase with molecular size. However, the chemical properties of all members in a homologous series remain remarkably similar because they possess the same active functional group. To systematically name the millions of carbon compounds, the International Union of Pure and Applied Chemistry, or IUPAC, developed a standardized nomenclature system. The name of a carbon compound is derived from its parent carbon chain length. 1 carbon is meth, 2 is eth, 3 is prop, 4 is but, 5 is pent, and 6 is hex. If the carbon chain contains only single bonds, we add the suffix -ane. double bonds add -ene, and triple bonds add -ine. If a functional group is present, it is indicated by adding a prefix or suffix to the name. For example, a 3-carbon alcohol is named propanol, while a 2-carbon carboxylic acid is named ethanoic acid. Systematic nomenclature ensures that every unique molecule has a single, unambiguous chemical name. A functional group is an atom or a group of atoms that replaces hydrogen in a carbon chain and determines the chemical properties of the compound, regardless of the chain length. The major functional groups include halogens like chlorine or bromine, which add the prefixes chloro or bromo. Alcohols contain the oxygen-hydrogen group, written as OH, adding the suffix OL. Aldehydes contain the carbonyl group at the end of the chain, written as CHO, adding the suffix -al. Ketones contain the carbonyl group in the middle of the chain, written as CO, adding the suffix -1. Carboxylic acids contain the COH group, adding the suffix OIC acid. These functional groups are the active centers of chemical reactivity in organic molecules. Carbon compounds undergo several characteristic chemical reactions. First, combustion. Carbon burns in oxygen to release carbon dioxide, water vapor, heat, and light. For example, methane combustion is highly exothermic, which is why it is used as a fuel. Second, oxidation. Alcohols can be oxidized to carboxylic acids using oxidizing agents like alkaline potassium permanganate. Third, addition reactions. Unsaturated hydrocarbons add hydrogen in the presence of catalysts like nickel or palladium to form saturated hydrocarbons. This process, called hydrogenation, is used industrially to convert liquid vegetable oils into solid vanaspati ghee. Finally, substitution reactions. Saturated hydrocarbons react with halogens like chlorine in the presence of sunlight, replacing hydrogen atoms one by one. Ethanol, commonly known as ethyl alcohol, is a volatile, colorless liquid at room temperature with a distinctive smell. Its molecular formula is C2H5OH. Ethanol is highly soluble in water in all proportions and is the active ingredient in all alcoholic beverages. However, consumption of pure ethanol, called absolute alcohol, is highly lethal. Chemically, ethanol reacts with sodium metal to release hydrogen gas, and heating it at 443 Kelvin with excess concentrated sulfuric acid dehydrates it to form ethene. Industrially, ethanol is a powerful solvent used in paints, varnishes, medicines like tincture of iodine, cough syrups, and tonics. It is also increasingly used as a clean-burning biofuel additive in gasoline. Ethanoic acid, commonly called acetic acid, has the molecular formula CH3COH. A 5 to 8% solution of acetic acid in water is known as vinegar, which is widely used as a food preservative in pickles. Pure ethanoic acid has a melting point of 290 Kelvin, meaning it often freezes in cold climates, which is why it is also called glacial acetic acid. Ethanoic acid reacts with absolute ethanol in the presence of an acid catalyst to produce ethyl ethanoate, an ester. This is known as an esterification reaction. Esters are sweet-smelling substances used in making perfumes and artificial flavoring agents. Reacting esters with sodium hydroxide converts them back into alcohol and sodium salt of carboxylic acid, a process called saponification, which is the chemical basis of soap making. Soaps are sodium or potassium salts of long-chain carboxylic acids, while detergents are ammonium or sulfonate salts of long-chain carboxylic acids. Soap molecules have a dual nature, a hydrophilic ionic head that is soluble in water and a hydrophobic hydrocarbon tail that is soluble in oil and grease. When soap is dissolved in water, the molecules arrange themselves into spherical structures called micelles. The hydrophobic tails point inwards, trapping the grease drop at the center, while the hydrophilic heads point outwards into the water. This micelle structure holds the oily dirt in a stable emulsion, allowing it to be washed away when rinsed. Detergents are superior to soaps because they do not form insoluble scum with the calcium and magnesium ions present in hard water. In this comprehensive lecture, we have explored the chemistry of carbon and its compounds. We studied covalent bonding through electron sharing and carbon's versatile nature based on catenation and tetravalency. We classified hydrocarbons into saturated alkanes and unsaturated alkenes and alkynes. We derived IUPAC nomenclature rules and analyzed functional groups like alcohols, aldehydes, ketones, and carboxylic acids. We investigated chemical reactions including combustion, oxidation, addition, and substitution. Finally, we studied the properties of ethanol and ethanoic acid and analyzed the micelle cleansing action of soaps and detergents. Review these structures and reactions to master organic chemistry. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension.